Hey folks. So chapter one is really is a review chapter in the most basic sense of the word. However, do make sure that you actually review this material and do problems and get that done soon, because pretty much every other chapter is going to use concentrations in some way and chemical measurements in some way. You really can't do anything in quantitative chemistry without concentrations or measurements of some sort, right? So if you don't have these down really well, you really need to make sure you get enough practice. These should be like, you could do these at 3 o'clock in the morning, half asleep, and you'd get them right, okay? They should not be something that requires a great deal of brain power and you're having difficulties figuring out. You really need to drill them until that's true. That's very easy to do. These are the basic SI units. Interestingly enough, a lot of people forget which is the SI unit, which is not. For example, Kelvin. Oftentimes people use Celsius and think that's the SI unit, or kilogram. Kilogram is the only one that has a prefix. That's a basic unit, which is the SI base units. So kilogram is actually the base unit, not gram. And it's Kelvin, not degrees Celsius. These are some of the derived quantities. These are based on the base SI units. You'll notice they're combinations of those other units. This is actually extremely useful if you know these, because you can do the math to get any value using the base units. And all those formulas that you may have memorized in physics, you didn't need them. You could have just known what a Newton is and, gotten rid of the units in it until you get what you want. Like if you want the acceleration from it, you just have to divide the weight, the kilograms. So it's actually very useful if you know these things. Again, same thing with joules. You would substitute that in right there. So it's meters squared, seconds squared here. Kilograms, meters squared, seconds squared. If you actually pay attention to these units, you can start drawing some interesting conclusions, which many of them are actually more recent, more advanced applications of physics and chemistry. So you can pretty much do all the work yourself if you wanted. These are the prefixes. Notice this prefix list goes way past where your general chemistry ones went. I'll be honest, I forget some of these sometimes, like zeta, iota. I just don't use them so little, I forget them all the time. Anyways, pretty much the maximum one I really remember is peta, and some days I remember exa, but zeta and iota I pretty much forget every time. These are the symbols, by the way, for those prefixes, if you're curious. Yes, there's formatting problems again, which is, what it is. Whenever you use the prefixes, again, they just mean that you've done this 10 to the negative 3 is now no longer 10 to the negative 3, right? That's because you've grouped that in as a prefix. Oh, this is messed up, isn't it? Okay. This should have been MPA right here, I guess. No, it's right. It's okay. This is just a conversion. Anyways, when you rewrite these, just remember, do it in scientific notation. It'll make your life easier. These are the different concentrations that are typically written. This is not an extensive list. It's not all of them. There's molarity, of course. Molality is actually sort of, and percent weight are typically the ones that people struggle with. So molarity, formal concentration, percent by volume, weight by volume, parts per million, parts per billion. All of those are divided by volume measurements. Or these aren't, I'm sorry, excuse me. These are not. The ones divided by volume here, and this, molarity and formal concentration. All of those are divided by volume measurements, and so are extremely easy to convert from one to the other, because they're all volumes. So the denominator is pretty much the same for everything, and there's a bunch of shortcuts you can use. However, molality is kilograms of solvent only, which means it's the odd duck out. It's always a little bit more difficult to convert it to anything else because that's only solvent, not the solution. Okay, so keep that in mind. Small m, molality, only kilograms of solvent. The moles of solute is obviously not difficult to do. That's something that's you probably won't have any difficulties with since you're used to it in molarity, and it's also easily converted to weights using the molar mass or formal mass, formal weight, whichever one you want to call it, depending on the system. The percent compositions can be interesting. In many systems, these percent concentration compositions actually end up being very similar. And that's because in many systems, it's dilute solutions of water. And so the weight and the volume actually end up being the same thing for the solution. If it is a dilute solution, meaning low concentration solution of water, because water's mass over volume, its density, is 1. So it has essentially a room temperature 1-to-1 ratio. The parts per million and parts per billion are ones people get tripped up all the time, but there's kind of an easy trick to remembering this and understanding this better. So the percent weight is parts per 100, okay? Literally, you're just taking the weight over the other weight, multiplying it by 100, right? The parts per million is the same thing, but just million instead. So you take the weight divided by the weight and multiply it by a million. There you go. Parts per billion is the same thing, just billions. So you take the weight divided by the weight and multiply it by a billion. And so really the weight over weight percent composition, parts per million, parts per billion, they're extremely similar numbers. It's just that you're scaling them differently. So you scale the percent is 100. That's out of 100, right? Here it's out of a million. Here it's out of a billion. And so these give you numbers that, even if they're very small normally, they're going to be whole numbers. So like 10 parts per billion is an extremely small concentration, but much, much easier to write as that 10 parts per billion than it would otherwise be. Weight, the percent compositions are, this is actually kind of a funny thing. In the United States, these are very poorly defined, oftentimes with little prints on the bottle, if they are at all, that are clear on clear. So you almost have to feel the label. It is incredibly difficult to tell sometimes if you're looking at a percent weight, or if you're looking at a percent weight per volume, or if you're looking at volume over volume. It is oftentimes not labeled at all. Okay? Weight over weight is actually, overall, tends to be sort of the more common one, kind of, except when it isn't. Unfortunately, I have to, there really isn't a, hey, this is an easy trick. It's just a bad system, okay? It's a system that people use and they don't really understand what they're doing, and so they don't label it at all. But anyways, this is actually what you've probably seen on alcohol containers, if you're curious, is percent composition, and proof is just double that number, if you're ever curious. Proof is just an easier way to determine that. Well, at least it was an easier way of determining that based on its burning for alcohol concentration. So anyways, this is parts per million. Again, it's the mass of the substance over the mass of the entire sample, and it's times a million if it's parts per million. Parts per billion would be times 1 billion. A million is 10 to the 6th. A billion is 10 to the 9th. ppm, it would also be milligrams per liter if you're in a dilute water system, or micrograms per milliliter, again, if you're in a dilute water system. I know this actually says if the density of the solution is 1, that is true. There are systems that a dilute water solution is the most common by far and away. 99% of your systems that are density of 1 are going to be dilute water solutions. There is almost no other examples, okay? There are very, very, very few, and you probably will never see them, that are a density of 1. This works out, by the way, because this is a 1 in 1,000. This is the prefix for 1 of 1,000. And this right here, for density, is 1,000 times what the density normally is, which is milliliters, right? Typically, this is grams per milliliter. And so you get an overall 1 million times difference between these than what they normally would be in a density. This is actually incredibly useful, by the way, if you remember this, because you can really speed up your calculations and not have to, do a lot of work. An aqueous solution that is 1,000 parts per million and Cu contains 1,000 milligrams of Cu per a liter of solution. Keep that in mind when you look at these fractions. They're the same thing as per. They're I get a lot of people that at the beginning of this class, they sort of struggle with the mathematical representation you would want to write it as when you're doing the math versus the word representation that you see in the problem or in real life. So please keep that in mind. One of the things I want to mention here is people get this in their head that, oh, I can just, do this conversion like this, a milligram per liter. That is what a ppm is, period. That's not true. Don't forget the density has to be 1, okay? It has to be a density of 1 gram per milliliter. If this is a solution that's made up in ethanol, that's not true. If this is a solution that's made up in anything but water, it's not true. If this is a solution that has a higher concentration than typically like 10%, that's definitely not true. Typically, you'd have to have a very low concentration, something in the fractions of a molarity, in the parts per million. Parts per billion will always be low concentrations, and it has to be low concentration for all species. If there's any high concentration species in it at all, the density is going to be different than 1, okay? And yes, it being lower than 1 is just as bad as it being above 1, all right? It doesn't matter which way it goes there. If it's not 1, density of 1, these are not true, okay? It will not be a simple conversion. A part per million will not be a milligram per liter or a microgram per milliliter. It only is true when the overall solution's density is 1. Make sure you actually try these problems and do them. You shouldn't really have any difficulties, I don't think. But let me know if you do. I can work out problems for you. I can either work through this one or I can work through the one, something similar to the homework. When you make solutions, this is actually one of those things that students really struggle with in lab, is when I just tell you to give me a solution with a stated concentration, students just get lost. And so the first thing you have to do is you have to sit down with your calculator and your paper and calculate out the volumes and concentrations. So if I state a concentration I want, you're going to have to get the concentration of the concentrated species, which would be like concentrated sulfuric acid, concentrated nitric acid. It may be a weight that you have to add to a volume. So you would take a weight of NaOH, which is little pellets, right? A weight of sodium bicarbonate, baking soda, and you'd weigh it out. You'd use your formula mass to figure out how many moles that is. You would put that into a graduated cylinder. You would fill it to a mark. Typically, you want to do these things as 100 milliliters, 50 milliliters, or 1,000 milliliters, because those are the containers we have, right? And so you would make a essentially arbitrary concentration as above the concentration you want to get at some point as your first solution. You would then use this dilution formula, which is a very simple dilution formula. M1V1 equals M2V2. This works for any volume-based concentration. So absolutely any volume-based concentration, whether that's percent, whether that's whatever, doesn't matter. As long as it's volume-based, you're good. This would actually also work for mass-based ones, but there's a caveat. The density would have to not change due to you diluting it. So if you already have a dilute solution in water or something, and you go to a slightly more diluted solution and that doesn't change its density, you could actually use this. It would work. However, if you change density because you're doing things that the volume isn't going to be changing, going to be changing, and that's going to change directly your concentration, that would not work if you change density. So keep that in mind. However, molarity is defined based on volume. That's why we like to use molarity in labs, is because molarity is moles per liter. It's already defined by the solution volume. It makes these change in concentration formulas extremely easy to do, because moles never changes, and the volume is what you're changing. It's the only thing you're changing. Only thing you have to worry about. Okay, so remember that this formula really is just looking at moles equals moles, isn't it? That's all it really says. It says the moles you put in equals the moles you get out at the end. And the volume you change is going to change the concentration due to that. So, nice and easy. This is an example of making a solution. It's exactly what I said before. Remember to always add what you're diluting first. So if you have a solid, add the solid first. If you have a dilute solution, add a concentrated solution you're diluting, add the concentrated solution first. Why is that? Well, if you fill it up first, the solid you put in, the concentrated solution you put in, it still has a volume. I know the volume isn't as much as you're going to end up with, but it still has a volume. So you'd always end up going over the volume you think you're going to get to. So remember, always add what you're diluting first, then dilute it up to here, and then finish it off slowly. Because if you go over your markings, you could not know what this is at all, and you'd have to restart and waste a bunch of chemicals. And you waste your time. So remember that. Always start with what you're diluting, then dilute it. Don't go the other way. Which, by the way, is another thing that people get into this lab and they have somehow not gotten from the other material stuff they've taken. So that is that. Again, this is just another example. Let me know if you have any issues with this. Try to work this out and do your homeworks. It really isn't anything that you haven't done before, but you've never done these self-motivated. Typically, they were heavily set up whenever we had you do them in previous classes, and so you might have developed bad habits by now. Anyways, you'll oftentimes have to use a concentrated, like concentrated HCl, concentrated sulfuric acid, concentrated nitric acid to make a solution. The bottles actually tell you the concentration and the density typically. If they don't, you can look those up fairly easily. They are published known quantities. After 37.2% weight by weight, HCl starts what's called fuming, and it will self-regulate its concentration by taking on water from the environment. So literally you can't get it above this concentration. It will just take water on from the air until it gets to at least this concentration. And then if you leave your bottle open and you don't cap it back up, it will actually dilute itself over time. So kind of an interesting side note. Same thing with sulfuric acid and nitric acid. You can't actually get them above certain limits at standard conditions. And so those are the concentrated, standard concentrated concentrations. The concentration of the concentrated form. That's a mouthful. Okay. So again, this is just more examples of how you make solutions. You don't really need all these examples. I just put them in here in case people want me to work more. Again, this is stoichiometry. You should remember stoichiometry. It's just a very convenient method to calculate or compute how much a reactant was consumed and what it should have produced. Keep in mind, though, this is always what it should have. It is a theoretical value if you calculate what it should produce or what it should have consumed. Okay? It is always a theoretical value. Things happen. You have impurities, they react with species in your solution, and you end up with a different product, and so you don't get the amount of product that you thought you should. You have conditions that don't allow full reaction, etc. So, always a theoretical number. Keep that in mind. Don't get tricked. However, there are tricks that we can try to push something to completion and try to set up situations where we will get what we would calculate through stoichiometry. This is sort of an example of that, where you can take iron in a tablet and you can force it through so it's all one species, and then force the conditions so the vast majority of it will react. You'll never get all of it, but you can get 99.9999%. Good enough. Okay? Again, the limiting reagent is always the one you run out of first. That should be something that you know already. I just want to make sure that you remember it because it's important. You can never get more than what your limiting reagent would produce. All right, that is it. There's not a whole lot of great stories that I thought of while I was reading this. Just sort of cautionary, hey, pay attention to this part of this deal. Let me know if there's anything you didn't understand from this chapter, or if there's any example problems you need. Honestly speaking, it's a review, and it's a review from a long time ago for you all. Very, very simple level stuff at this point. You have a great weekend. Take care.